Welcome to qnawire.
Okay, in this problem we have electron tunneling. So we have an electron with 5 electron volts of energy moving until it comes into contact with a potential barrier of width a fraction of a nanometer. And this barrier will have different heights for its energy. And we're going to compute transmission coefficients for each of these scenarios. This would tell us the probability of the electron tunneling through this barrier. And you notice that in order for it to be really tunneling, the potential, the height of this barrier needs to be larger than the energy of the electron. So classically, the electron should not be able to overcome this barrier, but quantum mechanically it can. And we would probably expect as the barrier gets taller and taller, the probability of it tunneling through goes down. So for equations, we were given a approximation formula for the transmission coefficient, which is a somewhat complicated expression. It's a decaying exponential, which involves k and g coefficients and L the width of the barrier, where g is defined as 16 e over mu naught, 1 minus e over mu naught, or u naught rather. And k is an expression involving the mass and the energy difference, all over h bar. So this is really just a plug and chug problem. We have everything. We know the mass. We know the relative energies. We know the width of the well. We have everything we need. We just need to plug everything in. So it's pretty straightforward. For the first case, we have a very, very small probability. Well, not that small. Fairly small. But it decreases from there. And this is found by just plugging everything in, computing k, g separately if you want, and then plugging it into this exponential expression for t. Or you can combine everything and do it all in one line. That can be more helpful when you're doing multiple sets of parameters, like this one. So as expected, we have t decreasing as the gap in energy increases. And that's it.